Hello, today we will be learning about the Doppler Shift. Now, you might be very familiar with the Doppler Effect, and the Doppler Effect happens whenever a car goes by, you really close, and you hear the you know that? That's the Doppler Effect. And it happens when you've got something, we'll just represent it with this dot, and it's emitting sound. And so when it emits sound, if it's at rest, it's all of the sound waves are going out equally. However, if it's moving forward at a fast enough rate, all the waves get sort of pushed back. Like this. So you get up close. And so the sound is being pushed back. And that means you get a higher pitched, and then it gets lower as it passes you. So you get the like that. If it was just standing next to you, you'd go so that was my sound effects for the day. But that's the Doppler shift, the Doppler effect. But what I'm talking about is the Doppler shift, and this happens when you're moving incredibly fast, like close to the speed of light fast in some occasions, and since, as you may know, light is made out of a bunch of different wavelengths, which I have shown right here. There we go. You can see, we can only see in this small section, but you can see the little wavelengths right here. And it just keeps getting smaller and smaller and smaller. So on. You can see it eventually goes down and such. But, yeah. We can only see bits of this, but light comes in waves, just like sound does. And so if you travel fast enough, your light waves get compressed. And so if I am heading towards you, they get compressed, and so they get smaller, and they go this way towards the ultraviolet. And so if I'm running towards you fast enough, I appear blue to you. Of course, I probably can't run that fast, because you have to be running near the speed of light for that to happen. And if I'm running away from you, though, my light gets stretched. Because, if you're over here, it's high-pitched, you're over here, it's low-pitched. This is the low pitch. So, I appear red on the other side, and that's how it works. However, what's cool about this is you can actually calculate what speed you have to be traveling to change certain light into different colors. So, here is the equation for that. We have this. Delta lambda over lambda little o right there equals V sub r over C. So instead of going one by one with each one, like I'm not going to explain delta, then lambda, then little o here, then the V, then the r, then the C, I'm going to explain them in little chunks. I'm going to explain to you by which side of the fraction it's on. So I'll do this side, I'll split into quadrants, this, instead of the entire thing, because this actually is different than you might expect. Now, if you've been studying some types of sciences, you would know that this delta right here, the triangle, isn't actually being multiplied upon lambda over here. It actually is a sign for change. And so lambda in this equation is actually the wavelength. So, delta lambda is the change in wavelength when something is coming towards or away from you. Delta, the little o next to it, is the wavelength when it's just sitting there, it's at rest. So, it's just it's emitting light, it's not emitting light. It's still emitting light, but it's just staying there, it's not moving or changing in color as it comes towards or away from you, it's just staying in the same place. V sub r, is the radial velocity. And this is when things get a bit tricky. So here's what's going on. If I have a positive radial velocity, that means the object is going away from me. If I have a negative radial velocity, that means it's coming towards me. And if the radial velocity is 0, that means it's going sideways. So this is something you want to remember in our next equation. C, if you remember from E equals mc squared, c equals the speed of light. Now there's another small equation within this equation that helps us out a bit, and that is lambda observed. So if I'm seeing it, I'm watching it, and it's coming towards me or away from me. So lambda observed, so the wavelength that's being watched, is equal to, I'm going to represent observed by OBS later, but just wanted to spell that out for you. Is equal to lambda at rest plus delta lambda. Okay? So, here you go. You have the change in the wavelength divided by the wavelength at rest is equal to the way it's traveling towards you, forward or backwards, or coming towards you or away from you. That divided by the speed at which that's going, divided by the speed of light. And this is really cool because in my next video I will be showing you how to turn a red light green using this equation. I'll see you there.